In the last video, where we first introduced logarithms, the main learning objective was to be able to switch from what's referred to as exponential form into what's referred to as logarithmic form. If you start out with something that kind of looks like this, we want to be able to write it in a form that kind of looks like this. I use the analogy of multiplication and division. If you start out with an equation that looks like this that has multiplication, even though you might be able to solve that equation in the form that it's currently written in, it's beneficial to be able to rewrite that in a different form, namely using division. In this video, I want to suppose we kind of more start out with logarithmic form. So to start out with an example, let's look at the log base 3 of 1/9. What I would like you to get by the end of this video is to be able to understand what number this is equal to. And really, I think there's two different ways you can figure out what number this is equal to. And I think this is one of those cases where it'll be beneficial to be able to do it both ways because there's merit to each of the different methods that'll end up being beneficial later on in the class. So the first method will be more like what we did in the previous video. The idea with the first method is you look at this and you're like, I just don't understand logs. That's unfortunate, but I do understand exponents because we just spent a couple sections talking about exponents. If only I could rewrite this in terms of exponents. Well, the way you can rewrite this in terms of exponents is, I'm trying to figure out what this thing is equal to. Let's give it a name. Maybe we call it x. What I now have is a logarithmic equation, and logarithmic equations, I'm able to change those into exponential equations. Note that before I gave it a name, before I called it x, I didn't have an equation, and without an equation, I can't change it into an exponential equation. But now that it is an equation, I can change it into an exponential equation. I know that the log base 3 of 1/9 equals x is equivalent to 3 to the x power equals 1/9. Maybe you're using this red box for that. The base down in the log becomes the base on the exponent, and the number right next to the log goes over on the other side of the equal sign, and the number that was on the other side of the equal sign becomes the new exponent. So I get this 3 to this x power equals 1/9. And then I stare at this thing, and even though the x isn't isolated, maybe I know enough about exponents that I can solve this. I can think about, all right, 3 to what power equals 1/9? Well, let's see, 3 to the second power equals 9. But I don't want 9, I want 1/9. I want the reciprocal of 9. So I guess 3 to the negative second power would be equal to 1/9. In other words, the log base 3 of 1/9 is equal to -2. And if you can follow all that, that's great. That's kind of one of the two ways I want you to be able to evaluate logs. This log base 3 of 1/9 is equal to -2. And one way we could get that answer is by giving it a name, rewriting it in exponential form, being able to stare at that exponential form and tell what the answer is, and that's already a little bit weird. I assumed that you could just go from this line straight down to this line. I kind of talked my way through it, but another method for getting from here down to here would be to equate the bases. We saw this a little bit in 4.1. We got 3 to the x on one side of the equation, and on the other side of the equation, if I could write this as 3 raised up to some power, well, 1/9 is 3 to the negative second power. I've now equated the bases, so I know that the exponents must be equal. That gets me this -2 as well. I don't mean to confuse people by showing lots of different ways. In fact, I'd argue that the way we went from this line to this line was just by thinking about how could we equate the bases. So I don't really think about this as anything new. I'm just trying to add this as one additional argument for how we got from this line to this line. At this stage, you can either be like, all right, so x equals -2. X was what I was looking for, so I'm done. Or you could think about this red box again. What I have here is an exponential equation, right? It looks like what's on the left-hand side here. B to the y equals x. Playing the role of the b is the 3, the y is the -2, and the x is the 1/9. So I can rewrite that in logarithmic form, and this 3 would go down here in the base, this 1/9 would go right next to the log because it's playing the role of x, and this -2 would go on the other side of the equation. So you can think about the way I got from this line to this line was switching between logarithmic and exponential equations using this red box, and the way I got from this line to this line was switching between exponential and logarithmic equations, again using this red box. I know that's a lot to follow this chain of logic, and you might be like, isn't there an easier way? And frankly, for this example, there is an easier way, but you want to be able to manipulate these guys so that you can deal with harder numbers and so that you can deal with them when you run into algebraic situations. But for this specific example, I'd like to show you a second way that you can evaluate this. So the first way, switching between logarithmic and exponential equations. The second way is to deal with this in its own right. What I'm saying is, if I started you out with this division problem right here, yeah, you could switch it into multiplication if you were so much better at multiplication than division, and then stare at this multiplication question and just tell that x must be equal to 10. But it'd be nice if this made sense in its own right. It'd be nice if you understood division to the point where you didn't always have to switch division into multiplication. You could deal with division. You're like 50 divided by 5. I understand that. That's 10. I'm done. Not even thinking about multiplication. Sort of the same logic here. Yeah, we could always switch logarithms into exponents because right now exponents are more familiar than logarithms, but it'd be nice if this logarithm had meaning in its own right. If we could just look at this and tell what the answer is, just like we can look at this and tell what the answer is. So in order to do that, we have to give logs meaning. The log base 3 of 1/9 is a question, and what it's asking you is this question. The log base 3 of 1/9 is just saying what power, we're always looking for powers when we're asked questions about logs, what power do you have to raise the base up to, the base is 3 in this case, to make it equal to 1/9? And if that feels very similar to what we were asking up here, that's great. It's all the same thing, just looking at it in different ways. You could rewrite these in exponential form so that you can see that really all this question is asking is what goes up here in the exponent. What power must you raise 3 up to make it equal to 1/9? What I'm saying, though, is it would be nice if logarithms made enough sense on their own right that you didn't have to think about, oh, I switch it into exponents to make it make sense. This has a meaning. It is this meaning. The power that I have to raise 3 up to make it equal to 1/9 is -2. This is a point where typically students need a lot of examples. 8 examples is what I ended up fitting in here. 8 log examples that would be nice if you could solve some of these. And I think they kind of get harder as you go. And I'd say that for most students at this point, if you can solve, I don't know, maybe half of them, you're doing fantastic. And then if you can kind of understand the answers to the other half, you got everything you're supposed to get out of this video. So this first one, the log base 4 of 16, we can solve this 2 different ways. One way would be to set it equal to x, and then to switch it into exponential form, and then to look at that exponential form and rely upon your knowledge of exponential form. But what I would like you to be able to do is just look at this and understand what it's asking you. And what it's asking you is, what power do you have to raise this 4 up to make it equal to this 16? Well, 4 to the second power equals 16, so the log base 4 of 16 is just equal to 2. What power do you have to raise this 4 up to make it equal to 2? That's a little bit less obvious, right? I don't think it's really easy to tell what you raise 4 up to make it equal to 2, but if you're really good with your exponent rules from a previous section, you might remember that fractional exponents correspond with radicals, so square roots, cubed roots, things like that, and negative exponents correspond with reciprocals. So often when you see fractions, you're going to be thinking negative logs, and when you see square roots, you're going to be thinking fractional logs. So back to this example, because the square root of 4 equals 2, if I take 4 and raise it up to the 1/2 power, I get 2. Therefore, the log base 4 of 2 is equal to 1/2. The log base 5 of 1/25, well, 25 is 5 squared, but this is not the log base 5 of 25. If it were, the answer would be 2. It's the log base 5 of 1/25. Fractions, think negative logs. The log base 5 of 1/25 is equal to -2, and that's because 5 to the -2 power is what equals 1/25. Maybe that's beneficial to have some justification for these. The reason this is -2 is because 5 to the -2 power would be 1 over 5 squared, which is the 1/25. Similarly, 4 to the 1/2 power would be the square root of 4, so that gets me this 2 right here. What about the log base 8 of 2? Okay, what power do I have to raise 8 up to make it equal to 2? Well, 2 cubed give me 8. Therefore, the cubed root of 8 gives me 2. Taking the cubed root of 8 is the same as raising the 8 to the 1/3 power, so the log base 8 of 2 is equal to 1/3. As you can see, these are pretty challenging. These take a while to wrap your head around. It's really easy to confuse the negatives and the fractions. That's why I'm writing out all these justifications, but don't feel like you have to do that. The log base 2 of 1, that's a tricky one. But think about what it's asking you. To what power must I raise 2 up to make it equal to 1? 1/2, right? Nah, 2 to the 1/2 power would be the square root of 2, which is not 1. The square root of 2 is the number you have to multiply by itself to make it equal to 2, and 1 multiplied by itself does not equal 2. Okay, then what is it? Well, what power can you raise any base up to make it equal to 1? Maybe you remember from our exponent rules that anything to the 0 power equals 1, namely 2 to the 0 power equals 1, so the log base 2 of 1 would be equal to 0. Log base 9 of 1/3, I think this is the hardest one we've seen so far, maybe the hardest one on this page, maybe H is even harder, I don't know. Log base 9 of 1/3 is tricky, but the way to think about it is the square root of 9 gives me this 3 down here. So you're thinking, oh, okay, the answer is 1/2. No, the log base 9 of 3 would be 1/2. I don't want 3, I want 1/3. I want the reciprocal of 3. This is going to end up being negative 1/2. If you have a hard time with that, the reason why is because 9 to the negative 1/2 power is the same as 1 divided by 9 to the 1/2 power, and 9 to the 1/2 power is the square root of 9. So this is the same as 1 divided by the square root of 9. And the square root of 9 is just 3. So what I'm saying is when you take 9 and raise it to the negative 1/2 power, you get 1/3. So the log base 9 of 1/3 would be equal to this negative 1/2. What power do I have to raise 9 up to make it equal to 1/3? The answer to that question is negative 1/2. And if you can see that, you are an expert with your different exponent rules, and that's really good. And if you can't, that's okay. If you're just at the point where you can kind of see some of these easier ones immediately, and on some of these harder ones, you have to switch it into exponent form to understand it, that's fine. Remember our analogy here. If you have an easy division problem, maybe you can just solve it. But if you have a really hard division problem and you're not so good with division, maybe you have to switch it back into multiplication to understand it if you're still learning division. It's the same idea down here. We're trying to understand logs, but we recognize that logs are new and it's going to take a while to get comfortable with them. And if you can just do the easier log problems now, that's great. And for the harder ones, maybe you have to rely back on your knowledge of exponents. That's totally fine. 2 more. The log base 5 of the square root of 5. Maybe this should have been higher up. I think this one's not quite as hard as f was, for example. If you recognize that the square root of 5 is the same as 5 to the 1/2 power, then all this is saying, this is going to be a weird sentence, is what power do you have to raise 5 up to make it 5 to the 1/2 power? Wait, what? What power do you have to raise 5 up to make it 5 to the 1/2 power? Well, 5 to the 1/2 would be 5 to the 1/2. I guess this is equal to 1/2. Because 5 to the 1/2 power just means the square root of 5, the log base 5 of the square root of 5 is just equal to 1/2. And then the last one, the log base 8 of 4. I don't even know how to argue this. Maybe I tell you the answer and then I can kind of argue where the answer came from. I think this is going to end up being 2/3. You're like, 2/3? No, it should be half, right? Because 8 times a half is 4. Right, but I'm not multiplying 8. I'm asking myself, what power does 8 have to be raised up to make it equal to 4? And you're like, 1/2, right? Nah, 8 to the 1/2 would be the square root of 8. And the square root of 8 is not 4. The square root of 16 is 4. This answer is not 1/2. It'll end up being 2/3. And the reason why it's 2/3 is because 8, when you raise it up to the 2/3 power, gives you 4. You're like, really? I don't quite see that. Well, think about what it means when we have fractional exponents like this. The one in the denominator is the root, and the one up in the exponent stays as a power. So you can either think about this as the cubed root of 8 raised up to the second power, or 8 to the second power, the cubed root of that. There's 2 different ways we can write these. They give us the same answer when we have fractional exponents. At the risk of being obnoxious, I want to refer back to this video that we had a little while ago about the different exponent rules that you hated at the time. It was so painful to watch, but maybe you're starting to see why we needed to go through these. Being really good with exponent rules is crucial to understand what we're doing in this section. When you have x raised up to the a over b power, there's 2 different ways we can write it. We can say it's the b root of x raised up to the a power, or we can raise up to the a power whatever the b root of x is equal to. Either of these 2 forms give the exact same answer. So I can either take the cubed root of 8 here, the cubed root of 8 is 2, and then square that number. 2 squared gives me 4. Or I could attack it the way I'm doing up here, where I first square the 8, and I get the cubed root of 64, that's 8 squared. And the cubed root of 64 is asking me what number, when I multiply by itself 3 times, gives me 64. The answer to that question is 4, because 4 times 4 times 4 gives me 64. That last one especially, but maybe some of the other ones as well. Even if you couldn't come up with that answer, that's fine. If you buy this justification, if you can follow the green, that's fine. Eventually we'll get to the point where we can follow the red. That's a lot of information. Logs, again, they're a pretty challenging thing when you first see them. Don't be too hard on yourself if you're a little bit overwhelmed right now. We'll just get some more practice with these different logs and eventually they'll make sense. I think this is a good point to end this video.